This is ELC111, Introduction to Electricity, and this presentation is on electrical noise. Now, in the presentation on amplifiers, we talked about a common mode voltage as being an input to the amplifier, and this common mode voltage is electrical noise. Electrical noise is simply defined as an electrical signal that interferes with the desired signal as shown in Figure 1. Now, these noise sources can either be internal to the circuitry, we call this intrinsic noise, and these noise sources can be external to the circuit, call this extrinsic noise. And these noise sources can be unpredictable. Examples of these are lightning, welders, motors, and included with motors are variable frequency drives and static discharge. And noise sources can also be predictable, such as 60 hertz and harmonics of 60 hertz. This comes from the power, the 60 hertz line power that comes into our electrical equipment. And it can also be radio frequency interference and crosstalk. And we'll define crosstalk later. Now, internal noise sources, again, are those that are inside the circuit. And examples of internal noise sources are thermal noise, also referred to Johnson noise. And internal noise is due to the random motion of electrons in resistors. So we think about a resistor and draw a little sketch here of a resistor. And at any temperature above absolute zero inside of a resistor, there's going to be electrons moving from point to point, just randomly moving about, helter-skelter, to and fro inside this resistive element. And of course, anytime we have electrons moving, we'll have voltage. So existing from or across the terminals of this resistor is going to be some AC voltage. And this AC voltage is a function of resistance and temperature. Now, another source of internal noise is shot noise, and shot noise is due to the variation in current through diodes and transistors. So we think about a simple PN junction as we would find in a diode or in a transistor, and of course we've got some P material up here, we've got some N material down here. And as we've talked about in previous presentations, electrons are flowing through this PN junction. And not all these electrons will travel through this depletion region at the same velocity. Some of the electrons bash into stuff, some of them fall into valence orbits, some of them just pass right through. Some of the electrons stop in here and take a little break, smoke a cigarette and chat with their little electron buddies. But again, not all these electrons are flowing through this junction at the same velocity. Therefore, existing from P to N is going to be some AC voltage. And there's really nothing we can do about this. It's kind of interesting that they came up with this name shot noise because this noise, when amplified in audio systems, reminded audio engineers, of the sound that was made when you would shoot a shotgun up in the air and the lead shot would fall on a tin roof. I guess electrical engineers spent a great deal of time out in the country shooting shotguns in the air. I'm not sure. And the third example of internal noise sources is called flicker noise. And flicker noise is really not really well understood as to what the source is. They just know that it exists in semiconductor devices. And flicker noise is a low frequency noise. Again, they sometimes refer to this as a 1 over F noise, that if we look at the noise voltage as a function of frequency, we would find that graphically this response looks something like this. So the noise is predominant down here in the lower frequencies. The noise is, of course, less, as you can see graphically, at high frequencies. Again, flicker noise is not really, that nobody understands exactly what the source is. They just know it's there. Now, external noise sources can be from natural origins, electrical storms, lightning, electrostatic interference. And of course, they can also be what are classified as electromagnetic interference, EMI. And this is due to alternating current in conductors. External noise sources can also be radio frequency interference. Radio systems radiate signals, and those signals can be coupled into the circuit. We'll talk about that later. And also there's a source called crosstalk. And what this is, that anytime we have alternating current going through a cable or a conductor, that energy can be coupled into conductors that are beside that conductor. And this is what they refer to as crosstalk. Now, looking at external noise sources, these noise can be generated when electric motors are turned on. And when we turn a motor on, what happens is there's a surge of current through a conductor, and that surge of current through a conductor creates a voltage, and that voltage can be introduced into our circuits. Now, one of the largest sources of external noise is due to fluorescent lighting tubes. Understand that current's flowing back and forth through a fluorescent lighting tube, and this energy can be transferred through space, through the air, into our circuits. And this is particularly troublesome because that energy is at 60 hertz, the same frequency as our voltage source or our line power. We can also introduce noise into our circuits through motor drive circuits, and these are called variable frequency drives, and we see a VFD noise imparted on the signal in figure 2. We can also get or have noise introduced to our system from lightning and electrical faults, which will cause arcing between contacts or between points. This is like little mini lightnings, can introduce noise into our circuit. Welding equipment, and of course static discharge. Now, static discharge can come from a lot of sources. As you know, when you walk across carpet or walk across a floor, depending on the shoes you're wearing, that your body can accumulate charge. And when your body gets close to a piece of electrical equipment, this charge will leave your body or leave the equipment and go to your body and cause a voltage spike, as we see in figure 2. And you know, static can come from a lot of sources, not just you walking across the floor. Believe it or not, when you drop a piece of paper onto a Formica tabletop and that paper slides just a little bit on the Formica, you can generate voltages in the tens of thousands of volts in that piece of paper. Picking up a styrofoam coffee cup from a Formica tabletop can generate tens of thousands of volts of charge, and even sitting down or getting up from a urethane foam seat or chair can generate tens of thousands of volts of charge in your body. And that's why you get shocked when you get out of your car and touch the metal chassis of the car, is the fact that your movement in that urethane foam seat causes a charge to be accumulated on your body. So how does the noise get into our circuit? Well, one of the most troublesome sources or methods of noise coupling is through what we call the ground plane. And anytime we have current flowing through a conductor, we'll have voltage. And in electrical equipment that's plugged into a wall outlet, there'll always be 60 hertz energy flowing in the circuit, especially through ground as a return path to the wall outlet. And this 60 hertz current will create a 60 hertz voltage on the ground of the circuit, which will impart this 60 hertz energy into all the circuitry in our piece of electronic equipment. Now, noise is also coupled through what's termed electrostatic coupling. And we hopefully remember from our discussion about capacitors that anytime we have two parallel conductors, we have a capacitance. And anytime we have voltage, that voltage can be coupled from one plate of the capacitor to the other plate of the capacitor, from one conductor to the other conductor. Now, this electrostatic coupling can be reduced through good circuit design, but understand the source or the coupling capability is there anytime we have two parallel conductors. Likewise, whenever we have current flow through a conductor, we'll have magnetic flux. And if we have two parallel conductors, then we will have, by definition, a transformer, in that when current flows through one conductor, it will create an expanding or contracting magnetic field, which can induce a voltage into the second conductor. Again, this can be reduced through good circuit design. Now, the other noise coupling source is through radio frequency radiation. And there's not really much we can do about this. We can employ some shielding to mitigate this to a certain degree, but it's difficult to do. That anytime we have radio frequencies generated, then conductors are going to act like antennas, and they're going to pick up these radio signals. And this is particularly troublesome in the medical environment, because, as you might know, there are a lot of wireless transmitters used for sending patient information back to a central location. For the EEG field, this is not so troublesome because these frequencies are in the hundreds, or these radio signals are in the hundreds of megahertz, so they're generally not that problematic for gathering low frequency information from the EEG leads. But understand that we will have almost always some high frequency energy present in our system due to radio signals, not only from the hospital but from nearby radio transmitters. Now, when we talk about noise, one of the metrics we use is called the signal to noise ratio, SNR. And this is just a way to quantify, to attach a number to the noise level in a system. And the signal to noise ratio is always expressed in decibels. Mathematically, the signal to noise ratio is 20 times the log of the signal voltage with respect to the noise voltage. For example, if we have 10 microvolts of noise voltage and 140 millivolts of signal, then the signal to noise ratio would be 82.9 dB. And we see examples of noise with respect to a signal in figure 4, and you can hopefully appreciate the fact the larger the signal, the greater the impact that noise will have on the desired signal or the information that we're transmitting. Now, a signal to noise ratio of 20 dB is not real good. This means that the noise is 1/10 of the signal. However, a signal to noise ratio of 60 dB or greater is a good signal to noise ratio. This means that the signal or the noise is only 1/1000th of the signal. Now, I've found this information on the internet, and this gives us a list of mechanisms or means of reducing 60 hertz noise in EEG measurements. And again, the 60 hertz noise is particularly troublesome in making EEG measurements because this 60 hertz is a low frequency, and it's getting close to the frequencies that the frequency of the information we're trying to measure, the brain signals, and it's hard to filter this out without filtering out the information that we want to measure. So this list, again, I've provided the web or the link at the bottom for you if you want to read more about this topic. But again, always use ground cables, use the same type of electrodes, always be sure and prepare the skin properly. Recommended usage of EEG electrodes is 10 to 20 times. After a period of time, the silver chloride layer will wear off. Always check, make sure the connectors are clean, and avoid using excessive paste, in that this can cause, will increase the chance of picking up 60 hertz interference, again, mainly from the fluorescent lights in the room. So this is this covered noise, electrical noise definition, and sources and mechanisms of coupling that noise, and lastly a means of quantifying noise with respect to the signal to noise ratio.